Okay guys, welcome back. So in the last video I talked to you about, I actually explained to you about the introduction of frictional forces, how frictional forces act on an object, and how we can define frictional forces at different instances, and how the frictional force behaves on when applying some force on an object. So that's the introduction to frictional forces which I described in the last video. So in this video as I told you, I will be describing about more complex topics on friction. So what it actually happens is that in the last videos I talked to you that in some experiments you will see that the frictional force, the limited frictional force is slightly greater than the kinetic friction force. So for some experiments, for some courses, you will see that when the force is increased, right? When the force is increased like this. Now, if I take a graph, right? If I take a graph, some graph like this, I'll take the force applied on this side and the static frictional force in this side, right? Force applied on this side and the static frictional force on this side. So what it actually happens is that when the force increases, the static frictional force increases, it also increases, right? So in the last video I talked to you about a table, right? In the last video I talked to you about a table. So what it actually happens is that I told you that when the applied frictional force is applied force is 0, frictional force will be also 0. When the applied force is 1, frictional force will be also 1. Applied force is 2, frictional force is 2. Like that, up to applied force is 5, the friction force will be also 5. So if you are considering the static moment or the static frictional forces against the applied force, the static frictional force will be equal to the applied force. What that actually means is that if you plot a graph in which this independent axis is on the applied force and the dependent axis or the y-axis is the frictional force, what it actually means is that if the applied force, I am talking about the static moments, right? If the applied force is equal to the frictional force, if you draw a graph, that graph will be a straight line that is 45 degrees inclined to the horizontal, right? If it is 45 degrees inclined to the horizontal, it will be inclined to the vertical as well, so its gradient will be 1, right? What it actually means is its gradient is 1. It's like if you are connecting points 0, 0, 1, 1, 2, 2, if you are coordinating points like that, you will get a graph in which y equals mx graph, because at 0 applied force, the frictional force is also 0, so its intercept will be 0. And if the y value in the static region, if the y value is equal to x value, that means its gradient is 1. If its gradient is 1, that means the tan theta or the tan value of the angle between the graph and the horizontal is also 1. So that happens when the value is 45 degrees. So the graph will be like this: y equals mx, which has a gradient of 1, right? Like this, right? So these are for the static moments. So at some force, I told you, at some force, so I'll take this force, some force here. At some force, the friction, there will be some frictional force, but beyond this limit, from here onwards, like this side, the static frictional force will not change, right? Even you increase this. Now say this force, in the last video I took this force to be 5 newtons, this is 0 newtons. I took this force to be 5 newtons, so I'll take the same in this video. If you're following this, it will be easy. So at 5 newtons, this force will be also 5 newtons. But beyond that, if you increase, as I told you, if you increase this force even by a decimal point or even by some fraction, this force will change, but this force won't change. So this is the maximum value, this is the maximum y value that this force can take, right? This is the maximum y value this force can take. So this is actually the moment in which the object starts to move, right? As I mentioned in the last video. So this is the static region, this is the point, this is called the frictional, limiting frictional force, right? Limiting FF. Right? Limiting FF, right? So this is the limiting frictional force. So if you increase the force, the applied force will increase, but the force or the y value of this graph will not change. So as I mentioned in the last video, for some experiments, you will experience that the values after this point is called the kinetic region, or the kinetic frictional force, right? So this is the applied force, kinetic frictional force. So as I told you in the last videos, for some experiments, and sometimes some books or some websites, everywhere they experience that the kinetic friction force is slightly less than the limited frictional force. So as I mentioned, even if the kinetic frictional force is slightly less than or equal to the limited frictional force, what it actually happens is that even though you increase the force from here onwards, the frictional force applied force, if you increase the applied force, the frictional force will be same. So that happens only when the graph is parallel to the friction applied force, like this. Graph has some parallel line. So I will take the same thing, same occasion in which the limiting frictional force is slightly greater than the kinetic frictional force. So as I told you, even if you increase it by a small decimal, even if you increase it by a small fraction, still the kinetic still it will be in the kinetic region. So if you are drawing a very sensitive graph, you will experience some force, but if you are drawing it to some general scale, what you will experience is that if you take the coordinates of this graph very closely, that there will be actually a sudden drop. Say if you are taking 5 here and the next point is 5.5, like that, what you experience is, even if you experience the kinetic friction, even if you increase this force by a fraction, what you will experience is that there will be a sudden drop. If you are drawing in a very sensitive graph in which you can even take fractions, you will experience that there will be a considerable drop. Now if I am drawing in the not in a scale or something like that, what I will experience is that there will be a sudden drop, right? Like this. And beyond this, I told you, now this is also in the kinetic, this is also still in the limiting region, Now this is a region in which it is a transition between the limiting graph. This point is the transition between the static region and the limiting region. This area, this small drop, a sudden drop on this graph, is the transition between the limiting region and the kinetic region. So what actually happens is that if you increase the force, the kinetic frictional force stays constant while the applied force increases. So the graph will be simply like this, right? The applied force increases, but the kinetic frictional force stays constant. So the y value stays constant, x value changes. So that is a graph parallel to the x-axis, right? So this is the simple graph. So this is the kinetic region. This is the static region, this is the limiting frictional force, this is a transition between the limiting frictional force and the kinetic region. So that is a very small region, right? Very small region. So as I told you, if you are drawing a very sensitive graph, you will not experience a sudden drop. There will be some considerable drop like this, right? Some considerable drop like this, right? A small, like a right angle triangle, and then it will go straight like this. But if you are not drawing to a scale, you will experience a sudden drop like this. So that is how the frictional force acts on an object. Now what happens when the frictional force is acting on an object? Now I'll take another object like this, right? I'll take another object like this. I'll take another plane like this and an object like this, right? Like this. So what actually happens is, now this object has some weight. Here. I'll take the mass as m, so the weight is mg. And I told you that in according to Newton's third law, if this force acts some force on this object, now this object is this is some flow or something. The flow is also an object. If I take this to be an object like this, right? This to be an object something like this, right? So this will be an object. The flow is also a kind of an object, although we don't consider it an object. So if you apply a force from this surface to this surface, according to Newton's third law, will also act a force on this object, right? Now what actually happens is that we are pushing the flow, right? Like if this is a plate and there's a spring like this, right? What actually happens is we are compressing the spring. We are putting some force to the spring and we are compressing it. So if it is the flow also, we are putting some force, though that is not observable. If you keep some object on the flow, that is not observable that the flow is going down, because the object's mass is very small compared to the flow. So this force will be a very small force to the flow. But what actually happens is that this force is pushing the flow or the plane in this side. It is pushing some force. So this flow will have will produce a force which is equal and opposite, because it doesn't want to change its equilibrium, right? So what it actually happens is that there will be another force in from which the flow is exerting on this object. So I'll take that as R, right? So if you are actually, what happens is, now mg and r, although they are parallel, they should actually not be linear. Linear means they should sometimes be may be not in this motion, not in the same line. But what actually happens is, if there's a distance between r and mg, this object will rotate, right? If I draw some from r from somewhere here, so there will be a momentum on this point, right? So r is here, mg is here, the object will rotate like this. Object will rotate like this. So r is also acting. If this object is stationary, now if you keep some object on the earth, you will not experience that the object is starting to rotate. So what it actually happens is that to produce a zero torque or zero rotation, right? Zero torque actually. What it actually happens is that r is also linear to mg, like this, right? Linear to mg. So there's no distance between these two forces. So the r and mg acts from the center of mass, right? Center of mass. R is actually perpendicular to this plane and the object. Mg is also perpendicular to this plane, right? So what actually happens is that r is produced like this way, right? So now this object is initially stationary or initially at rest. So what if I put some force? Now consider this plane to be frictional, not frictionless. This is frictional. So what if I put some force F here in this direction? If in this direction, what it actually happens is that if this is frictional, as I told you in the last video, because the object is initially at rest, there is no friction on this object. If I increase the force, if I put some force, if I put a non-zero force or a net force on this direction, now if there's a system of forces, even if this need to be horizontal or vertical, if I even put some angle force, there will be a net force in this direction. So what actually happens is that, considering this object is not lifting into this direction, there will be a frictional force in this direction. Frictional force in this direction. Now in the last video I told you that there's a maximum value that this friction can take. Beyond that value, the applied force will be greater than the frictional force, and the object will accelerate in this direction. Considering the object initially at rest, there will be a velocity and a displacement of the object within a given time. So what it actually happens is that we have found from experimental data that at the limiting occasion, right? At the limiting occasion, the frictional force, right? At the limiting occasion, the frictional force applied on this object is directly proportional to the value of r. So r is sometimes also called the normal force, right? This is called the normal force in some notes, right? Normal force. That's actually not necessary. At the limiting occasion, we have found from experimental data. Now we can prove it in an experiment. If you are doing some experiment on this theory, you can prove that, right? I will not prove it here, right? So the frictional force is directly proportional to r, right? What it actually happens is that if F is directly proportional to r, F by r is a constant, right? Is a constant k, right? Constant k. So we have found that this constant changes when we change the plane, right? Now say this is initially the block is wood and this plane is concrete, and if we change the plane to be something like concrete, if you change it from to like steel, right? Steel or even another wood, what it actually happens is that this ratio between Ff and r, or the value of k, changes. So that is actually a unique quantity that is specific to these two surfaces. So The value of K between wood and concrete will not be equal to the value of K between wood and wood, or value of K between wood and steel, or for any two surfaces. So the value of K is unique to these two surfaces. So we also call this as mu, which is called the coefficient of friction, right? This is called also as the coefficient of friction. So the coefficient of friction, so we call it coefficient of friction, coefficient of friction. So the coefficient of friction, as I mentioned, is unique to any two surfaces. So if you change the surface, the coefficient of friction or the value of K also changes. So if Ff divided by R is equal to mu, Ff is equal to mu R. So this is a very important relationship when you are considering frictional forces. Ff is equal to mu R. But what actually happens is that this is only to the limiting, right? This is only to the limiting condition. Now you may argue that when you, according to this graph or to the data that I presented in the last video, then the limiting force, beyond the limiting force, we will have the kinetic friction. The kinetic friction also doesn't change when the applied force is changed, right? So the kinetic friction doesn't also change. So in some occasions, if you are given the kinetic friction, right, you can also put F kinetic equals mu R, right? F kinetic equals mu R. But for most occasions, only in some occasions, but for most of the occasions, the kinetic force is smaller than, as in this occasion, as in this example I have taken to draw this graph, the kinetic frictional force is slightly smaller than the limiting force. So what actually we have done is that we have defined the frictional force, the frictional F equals mu R or F equals mu R, to be at the limiting frictional force. So at some instance the limiting frictional force may be equal to the kinetic friction force. So at that instant you can put, but for most instances you cannot put Ffk equals mu R. So what actually happens is that either you have to be given that the limiting frictional force is slightly equal or actually equal to the kinetic frictional force, or in the problem you should have been given that the limiting frictional force on this object is this time, right? So there will be some value. So if you are considering the static moment, static frictional force, the static frictional force is not directly proportional to R, so there will be no ratio like Ff by R equals K. So because the static frictional force varies with the applied force, it is not a constant with the applied force. For a system it will be a constant, but we are taking the static frictional force not at a system like the limited frictional force or the kinetic frictional force. So what we are actually taking is that the static frictional force changes with the applied force, so we cannot derive a direct relationship. So if you are given some static frictional force or the coefficient of static friction, the static frictional force, you cannot derive such a relationship. So that is the general derivation or the relationship between the frictional force and the normal force. So in the next video I will be talking about how we can apply these theories in the real world. See you then.